Hello and welcome to today's webinar, Developing Measurement and Analysis Systems. My name is Rob Gressley and I'm an application engineer with MathWorks. Joining me today are Steve Crane and Neil Hoffman. They are application engineers with Keysight Technologies. Today we're going to give you an introduction to MATLAB and using it to develop measurement systems with Keysight Instruments. I'm going to start off by giving you an introduction to MATLAB as well as an overview of using MATLAB with Keysight Instruments. And then Steve and Neil are going to jump in to give an overview of Keysight's instrument lines, followed by some application-specific product demos, such as waveform generation, real-time spectrum analysis, IQ data capture, and so on. I'll wrap things up at the end with a summary, and then we'll also have some time for a question and answer session. So let's jump right in and discuss MATLAB to get started. So MATLAB is a leading environment for technical computing. It's a software environment as well as a high-level programming language that's really designed for data analysis, visualization, and algorithm development. Over 1 million scientists, engineers, and users worldwide make use of MATLAB. MATLAB also comes with a variety of toolboxes, including toolboxes for interacting with hardware, such as data acquisition devices or instruments, as well as toolboxes for performing different analysis tasks, such as signal processing, image processing, optimization, statistics, and so on. A wide range of areas there. During today's webinar, we're going to be focused on using MATLAB with the Instrument Control Toolbox to work with Keysight Instruments from MATLAB. At a high level, this is a typical workflow that people use when they're interacting with MATLAB to perform a particular task. They might want to get access to some data from a variety of sources, including different types of file formats, other software applications, hardware like sensors or instruments, or they may also have some equations or models that they'd like to bring in to a analysis environment. And MATLAB is an ideal analysis environment for exploring your data and creating new analysis methods and algorithms based on it. So MATLAB is a tool used for data analysis, mathematical modeling, algorithm development, and even application development. And then typically when people are done working with their data in MATLAB, they'd like to share the results of what they've done with the rest of the world. And that could come in form of a report, an application, or just some design values to pass on to other tools later on in the process. Our focus today is mainly going to be on using MATLAB to interact with hardware, and in particular using MATLAB to extend the analysis capabilities of the Keysight instruments. So to make this workflow a little bit more tangible, I'd like to give you a quick overview of the MATLAB environment itself with a demo. So I'll give you an overview of the MATLAB desktop, writing MATLAB code, and then also communications with hardware. So I'll jump into MATLAB right now, and this is the MATLAB desktop, which you'll see when you first start up MATLAB. Fundamentally, MATLAB's a command-driven language, so you can interact with MATLAB from the command window, typing in mathematical statements or some basic programming commands, and quickly interact with MATLAB, prototype, try things out. From the command window, I can also call scripts and functions, which are collections of MATLAB commands that I've saved and I'd like to recall for later. So I'm going to go out and call this function called collect data that I've written previously. This function actually uses some commands in the data acquisition toolbox to go out and collect 1 second's worth of data from a test setup that I have. And after executing this function, I'll notice on the lower left some new values here in my MATLAB workspace. These new variables in the MATLAB workspace are variables that I can now interact with, look at, plot, and perform calculations on them. So for instance, I'm going to take a look at my signals here in and out as a function of time. I'm actually capturing data here from an analog filter. So I'm looking at the input signal to the filter and the output signal from the filter and plotting those as a function of time. So I can select the values in my workspace and go up here to this Plots tab and see all the different ways MATLAB has to plot the data I've selected. So let's just do a simple time series plot where we can see that my blue signal is the input, the red signal is the output. So it looks like what I'm looking at here is a low-pass filter. As the frequency of the input signal is increasing, the amplitude of the output signal is decreasing. And now I can take this plot and I can interact with it, zoom into a particular area, pan around. I can add in data cursors or select data points using a brush. When I zoom in here, we see something that's kind of interesting. We see that the signals don't line up exactly with amplitude. So I should have a 0.5 volt amplitude here, but there's actually some offset being introduced on one or both of these channels. So this is something that may affect my analysis later on. So I might be interested in removing this offset. So I can manipulate my data in MATLAB from the command window as well. So let's take a look at the input signal. I can calculate the mean of that input signal and then subtract that value from the rest of that in signal. And the effect of this is going to be removing any type of DC offset that might exist on this particular signal. So I'm going to do that with my input signal as well as my output signal. And now I have these new entries here in my MATLAB workspace called ins and outs, which represents those signals with the offset removed. And now I have an updated plot showing these new signals. And if we look at the zoomed in portion of that signal again, we see that the values here do make a little bit more sense. Prior to performing this operation, the output signal actually had a higher amplitude than the input signal, which shouldn't make sense in this particular case. But after removing those offsets, we get values here that are much more reasonable. You may have noticed that as I was creating these plots, MATLAB was putting commands here in the MATLAB command window, allowing me to recall that plot for later. I can now recall those commands for later by looking at the command history, which has been keeping track of all the commands that I've been typing as well as the commands that MATLAB puts there. So I can select commands that I'd like to be able to repeat and quickly create a MATLAB script from those commands. A script is a collection of commands that you can execute as one step or one program. So now I have a MATLAB script that I can run. And it's going to execute each step in that process, including collecting the data, doing the analysis, and generating the plots. So typically this is how people interact with MATLAB on a daily basis. They'll be working in the command window or within a MATLAB app, trying things out, experimenting with different things, and then once they've decided on a process that they'd like to automate, they can quickly combine those into a MATLAB script to automate the process. So that should give you, a high-level overview of what MATLAB is in a typical MATLAB workflow. Steve and Neil in the next section will go into more detailed, more involved, and more application-specific examples using MATLAB specifically with Keysight Instruments. Going back into the slideshow. Before I pass it off to Steve, I'd like to give a really quick overview of using MATLAB to control Keysight Instruments. MATLAB has several toolboxes actually for interacting with hardware. Today we're going to be focused on the instrument control toolbox for working with standalone instruments. We also have a toolbox that works with data acquisition devices, as well as image capture devices or the vehicle networks. For more details on any of these toolboxes, you can also visit the MathWorks website for more information on any of these toolboxes. The instrument control toolbox is what we'll be focusing on today, and it can be used programmatically to configure, control, or transfer data with a wide variety of instruments. The instrument control toolbox offers support for common communication protocols such as GPIB, LAN, VISA, and USB, as well as different instrument drivers, including MATLAB's own instrument drivers and industry standard drivers such as IVI or VXI plug-and-play. The advantage of using drivers is that you can replace low-level instrument programming with code that's more readable. Finally, the instrument control toolbox also has a MATLAB app for interactively detecting and controlling instruments. Furthermore, that app will automatically generate MATLAB code for you, making implementing your instrument connectivity a little bit easier. Now, Steve and Neil are going to give several examples of using MATLAB and the instrument control toolbox to interact with Keysight Instruments. First, Steve is going to start out with an overview of Keysight Instruments. Steve?
Thanks, Rob. Before I begin my overview, I wanted to briefly discuss our new company. For those of you who may not be aware, Keysight Technologies is made up of what is formerly known as Agilent Technologies Electronic Measurement Group. As of November 1st, 2014, we are an independent company. Agilent continues on as a life sciences and chemical analysis company, and Keysight is going to be 100% focused on addressing your needs in electronic design, test, and measurement. So while technically we are a new company, we have 75 years of experience in this area, with our legacy going back to the founding of HP back in 1939. Today as Keysight, we continue to have a huge product offering covering your electronic measurement needs from DC to light. And MATLAB can be used to enhance the measurement capability and to automate all of these instruments. However, today I'm going to focus on the instruments that MATLAB is most commonly used with, and these include our vector signal generators, our arbitrary waveform generators, our signal analyzers, and oscilloscopes. So let's start with our vector signal generators. VSGs are used to create a wide variety of complex signals. Here you see our current offering of VSGs, including the X series made up of the EXG and the MXG, and the PSG, our highest performing vector signal generator. The MXG offers superior spectral purity and a modulation bandwidth of up to 160 MHz when using its internal baseband generator. The E8267D PSG provides frequency coverage up to 44 GHz and up to 2 GHz of modulation bandwidth when paired with an external baseband generator. MATLAB is commonly used with these products to create complex waveforms used in signal simulation, and for your convenience, it's possible to buy MATLAB directly from Keysight as an option to these products. You can use the Keysight model number N6171A to do this. This slide shows our high-performance arbitrary waveform generators. On the right side, you see our highest performing AWGs, including the M8190A and the M8195A. The M8190A offers exceptional spur-free dynamic range, offering operation at 14 bits in 8 gigasamples per second or 12 bits in 12 gigasamples per second. The M8195A offers sample rates of up to 65 gigasamples per second with a 20 gigahertz analog bandwidth. These products are also commonly used with MATLAB to create complex wideband signal environments, or they can be used to stress high-speed digital buses. I will be demonstrating an example MATLAB program that's available for use with these generators. It provides a graphical user interface to make it easy to download waveforms, as well as the ability to apply waveform corrections to account for the non-ideal performance of the hardware. Here is our X series signal analyzer family. It includes everything from our low-cost CXA to our high-performing PXA, and the latest member of the X series family, the UXA. The UXA uses proprietary technology to give us superior phase noise performance, as well as up to 510 MHz of real-time bandwidth with spur-free dynamic range in excess of 75 dBc. MATLAB is commonly used with these analyzers to create custom applications and displays, to help you analyze newer or proprietary modulation schemes, as well as to let you automate measurements and take advantage of MATLAB's advanced visualization tools. Again, MATLAB can be purchased as an option for these products for your convenience using the Keysight model number N6171A. Keysight also has a comprehensive modular product offering. These products require external software in order to take measurements. Now, MATLAB can provide an interface to all of our modular products, but it's especially complementary to our PXI arbitrary waveform generators, digitizing scopes, or our PXI vector signal generators or analyzers. And finally, we have our oscilloscope offering. We have low-end scopes in a handheld or benchtop form factor, and we have our two main line of scopes, the Infinivision and the Infinium family. The Infinivision family now covers up to 6 GHz with the introduction of the 6000X series, and the Infinium family has coverage of up to 63 GHz of real-time bandwidth. This family also includes the Infinium S series, which is the industry's fastest 10-bit high-resolution scope. The Infinium series also offers the N8806A user-defined function feature. This feature allows you to use MATLAB to develop custom analysis functions and display the results as live updates directly on the scope's display. Neil will be demonstrating this function later in the presentation. Okay, so let's move on to our product demonstrations. So I'm going to go through 3 demonstrations for you and then pass things over to Neil. The 3 demos I'm going to do consist of using 3 different MATLAB applications, and the intention here is to show you how MATLAB can be used with your test equipment to enhance your overall measurement capabilities. So the first demo consists of using a utility called IQ Tools. IQ Tools is a real nice example of how MATLAB, along with its optional toolboxes and the Keysight instrumentation, can be used to create a powerful signal creation solution that's easy to use. This utility works with the M8190 and the new M8195, as well as other Keysight waveform generators. The program makes it easy for you to connect to the hardware, create waveforms, download and play them, and it also provides an automated process for measuring the hardware impairments and then pre-distorting the waveforms to correct for those impairments. This example is available for download at our website. So the setup I'm going to be using, you can see over to the right, it consists of a 32 GHz X series scope that's going to be used to analyze signals created by the combination of the M8190 wideband signal generator and the E8267D vector signal generator. The combination of the M8190 and E8267D give me up to 2 GHz of modulation bandwidths on carriers up to 44 GHz. Now the challenge here when you're generating waveforms this wide, is that the hardware impairments become very apparent, and so we need to do something about that. And this utility provides a couple of ways for dealing with it. It can measure the amplitude flatness by generating a multi-tone signal and then automating measurements with a spectrum analyzer. And this does a nice job of correcting for the amplitude flatness or non-flatness of the setup. However, there's some applications out there where it's necessary not only to correct for just the amplitude, but we also want to correct for the phase response of the hardware as well. And that's what I'm going to show you today. So the process of doing that is to create a wideband digitally modulated waveform and then use the 89600 software to demodulate and determine the complex frequency response of the setup, which consists of both the amplitude and phase response. And then the utility will go ahead and correct for these correct the waveform for both the amplitude and phase response of the setup. Okay, so let's switch over to MATLAB. You can see I already have MATLAB loaded, and I am pointing to a directory here that contains my IQ Tools utility. And to start up the utility, I simply have to type in IQ main, and you can see now I have a graphical user interface that pops up, and I can just use that from here on out. So the first step in the process is to configure a connection to your instrument. As you can see, the utility supports the M8190, the M8195, and a host of other Keysight signal generators. I'm going to be operating with the M8190 in 14-bit mode, and I'm going to be connected to a driver that's running on a remote PC using a LAN interface. For this demonstration, I'm also going to be using the PSG set to a carrier frequency of 10 GHz, so I'm going to put that value in here. So you can see this utility provides means for generating multi-tone signals, digitally modulated waveforms, radar signals, even serial data generation for testing high-speed serial digital buses. But I'm going to start out by generating a digitally modulated waveform. And the digitally modulated digital modulation utility here provides means for putting in symbol rates. I'm going to make a really wide band signal. I'm going to create a signal that is with a symbol rate of 2 gigasymbols per second. And I'm going to leave the modulation type at 16 QAM and pretty much leave everything else the way it is that you see here. So I'm going to go ahead and download the waveform, and I have the VSA utility opened up here, and you can see the waveform's playing, but the quality of the waveform, in fact, let's just show the constellation diagram. So you can see I'm barely able to demodulate this signal. There's enough impairments here that make this signal very hard to demodulate. So what this utility will do now is it'll turn on the adaptive equalizer of the 89600 software to measure the complex frequency response. So I'm going to go ahead and hit the calibrate using VSA button. And you can see it's taking control of the VSA software. It's turning on the equalizer, and as you can see, those constellation points are converging nicely to some nice tight constellation points. And my EVM has dropped somewhere below 2%, which is pretty respectable for a 2 gigasymbol per second waveform. So I'm going to go ahead and click OK. So the utility then takes that complex frequency response that the VSA has measured, and it's applying that to the inverse of that to the waveforms in order to correct them. And you can see the correction here that was determined. I have both magnitude and phase plotted here, and you can see for my magnitude, it's probably maybe about plus or minus 5 dB across the 2 gigahertz span of amplitude flatness. In terms of phase flatness, that's much worse. That's going to be, looks like more than 30 degrees peak to peak of phase flatness here that's being corrected for. So you notice now the adaptive equalizer is not on. I'm getting the same 2% EVM that I was able to get before with the equalizer. So now that these corrections have been stored, I can actually apply them to other waveforms. So if I'll do that by bringing up IQ Tools and going to the radar signal. And I'm going to pretty much leave everything as default. We're going to generate a pulse width of 2 microseconds and a frequency chirp of 2 gigahertz here. So essentially over the same frequency range I just calibrated for, I'm going to generate this radar signal. So I'm going to go ahead and download that. And I need to recall other setup file. So here you can see this is the I'm triggering on the pulse, and you're looking in the frequency domain here. You can see that it's certainly not flat. We've got some ripple across the band. That ripple is apparent both in the time domain plots as well. So this is the amplitude as a function of time, and then you can see the real and the imaginary waveforms, the I and the Q waveforms, as a function of time as well, with considerable ripple on that. At a 2 gigahertz wide chirp, you know, the frequency and phase response still looks pretty much as expected. You can't really see the impairments here, but they're certainly apparent in the I and Q as a function of time waveforms. So if I go back to the radar section in IQ Tools, I can enable the correction and apply the correction now. And what you'll notice is now my response is much flatter in both domains here. In the frequency domain and in the time domains, I have a nice flat response here, which would be something more along the lines of what you would want for testing high-performance radars. Okay, so for the next demonstration, I'm going to be showing you the real-time spectrum recorder application, which is a MATLAB application that can actually be purchased as an option to our PXA or MXA analyzer. And this application complements these analyzers when they're operating in real-time mode. And you would use real-time mode to understand highly dynamic signal environments, or to find those or discover those highly elusive signals that could be present. And what this application does is it actually records the density display output of the real-time analyzer and can record those display outputs for long periods of time, for minutes or even hours, to allow you to document or to understand the timing relationship between signals that might be spaced far apart in time. So in the real-time analyzer itself, can show the timing relationships between some signals, but really only over a brief period of time when operating in real-time mode. So you can use this analyzer or this recorder feature to look at longer periods, and then you can scroll back and forth through the history of those screenshots essentially, and use markers to understand the frequency, amplitude, and even the timing relationship between the two. So to demonstrate the real-time recorder, I have a remote desktop connection to a PXA analyzer that's already operating in real-time mode. So in real-time mode, the analyzer is not sweeping like a swept-tune spectrum analyzer, but it's parked at a specific frequency of interest. In this case, I have it tuned to 2.44 gigahertz, which is the band where wireless LAN signals and Bluetooth signals operate. While we're parked at this center frequency, the analyzer is digitizing up to 160 megahertz of bandwidth and is performing up to 300,000 FFTs per second in hardware in order to keep up with this highly dynamic environment. And you can see here we got some wireless LAN traffic, we got some frequency hopping signals, and to make this spectrum a little bit more cluttered, I can turn on a search feature of my cell phone. You can see these Bluetooth signals that are popping up here. They're pretty large frequency hopping signals that are interfering with everything. Now, in order to demonstrate the real-time recorder, I have MATLAB operating on this signal analyzer. So I'm going to bring up MATLAB there and go to the Apps tab where I can fire up the real-time recorder application. And what this real-time recorder application will allow me to do is it will allow me to set up the analyzer in real-time mode, choose the center frequency, which is already set to 2.44 gigahertz, choose the span that we're going to make our recording over, and also the acquisition time that we're essentially going to accumulate the FFTs for up to 200 milliseconds and update the display at that point in time and record the display output at that point in time. So I'm going to go ahead and start the recording, and I'll turn on the Bluetooth function on my cell phone again so we get those interferers that pop up, and then I'll just hit stop recording and we should be able to view the recorded waveform now. So if I hit the playback button, it'll scroll through the data that we recorded, and you can see there was some activity going on there. You can grab the scroll bar and go back in time and look at different events, use a marker to measure the frequency and amplitude of those events, and obviously this will help you also understand the timing relationships of everything that's happening. So the real-time recorder again can be used to record up to minutes to hours of the density display output. All right, I'm going to shut this down for later and go back to our slide presentation. So in summary, the real-time recorder can be ordered as an option to the PXA or MXA analyzer. When you order this option, you get the source code that you see here, so you have the capability of modifying the graphical user interface or any of the other code that was used as part of the analysis. You also get the MATLAB software environment that's required to run this application. Okay, so the last demonstration I'm going to do before I hand things over to Neil is I'm going to demonstrate an application that's available from our website. It's written in MATLAB, and it shows you how you can capture IQ data that's collected from our analyzer, modify that IQ data, and then download the modified signal into a vector signal generator for playback. Now for this demonstration, my laptop is connected to an MXG vector signal generator and a PXA signal analyzer using a LAN interface. So here is a simplified block diagram of our analyzer when it's operated in IQ basic mode. The incoming signal is downconverted into an IF signal, which is then digitized. That digitized signal is further processed to produce digital I and Q data that's sent to the analyzer's memory. Now the MATLAB application is going to capture data out of that memory and transfer it back to the PC where it can be analyzed. Now once I have that IQ data as a function of time, I really have all the information I need to analyze the signal. The amplitude of the signal can be calculated by taking the square root of I squared plus Q squared. The phase of the signal can be calculated by taking the arctangent of Q over I, and any frequency modulation on the signal can be determined by differentiating phase with respect to time. And MATLAB is a tool that can easily handle all these types of computations and help us to either display or analyze the data further. So for the first part of this demo, I'm going to use this application to perform a basic IQ data capture. The utility will allow me to either visualize the capture directly or to save the IQ data to a file to be processed further. This application will transfer the data from the signal analyzer memory to the PC using a block data transfer method, which ensures a reliable and efficient transfer, even if you have long data captures. Alright, so let me go back to MATLAB here, and I'm going to go to the Applications tab and open up the Deep Capture and Upload utility. And I'm just going to go to the capture mode here, and within this mode I can make a connection to my signal analyzer. I can specify the center frequency and the span. I can also specify the requested capture time, which I'm going to make that 10 milliseconds to make things a little more efficient. And let's take a look at our signal analyzer and let's set this up for this demonstration. So first of all, I'm going to put this into spectrum mode, and I also need to disconnect my antenna that I had connected, and I'm going to connect the signal generator directly to my analyzer. There's the signal. And let's take a closer look at that. You can see that this is a digitally modulated waveform that we're going to use to capture. And I'm just going to visualize this first. So let's perform a capture. And you can see the analyzer switch modes. We grab the time sample that I asked for, and you can see the frequency and time domain data there. Okay, so let's save this same capture to a file next. So I'm going to perform another capture. Get prompted to enter a file name. Let's just call this test1. And now I can go back to MATLAB and we can load that file that I just captured. I find it down there. And there you can see this is the IQ data that was just captured, and if we just want to do a quick plot on that, you can see I have what kind of looks like a QPSK constellation diagram that you can see there. So again, this utility does a deep capture and allows you to save the data to MATLAB to be further processed. So now that we can capture that IQ data, we can take it a step further by modifying that data and then downloading the modified data into a vector signal generator to be played out. So with that modified IQ data loaded into baseband memory, the vector signal generator will convert it back to analog and then modulate that onto a carrier using an IQ modulator. So the same application has the ability to add signal impairments and to do this download to the signal generator. So let's go back to MATLAB, and I'm going to open up the deep capture and upload with impairments portion of the utility. And again, I need to make a connection to my signal analyzer and to my signal generator this time. I'm going to do this at same frequency and for the same amount of time. And we'll turn on some fading. So I can turn on maybe 3 channels of fading, and we can make that maybe 30 dB of fade. I can also turn on some Doppler as well. So if I go ahead and run this, we'll do another capture, you'll notice. And then what we do is we modify that signal by adding the fading and Doppler shift, and you can see what that would look like here. And then that signal should have been sent back to our vector signal generator so we can look at it again on our analyzer. It looks like we have something there. So there you can see our signal is now shifting in frequency due to the Doppler shift, and then we have those suckouts caused by the fades that we described. Okay, so I'm going to pass things back over to Neil, and he'll take things from here. Thank you.
Thanks, Steve. Now we're going to talk about a couple different ways you can use MATLAB with Keysight oscilloscope products. One is an application that you see up on the screen right now, the N8832A frequency domain analysis application, which is an application that runs and executes in the MATLAB environment and does analysis in the frequency domain. Then we'll talk about the N8806A user-defined function, which is an application that executes and runs under the Keysight Infinium oscilloscope software environment and does analysis primarily in the time domain. And we'll also give you a quick demo of each application. So we'll start with the N8832A frequency domain analysis application. You see the app launch screen on your screen right now. Again, this application installs under MATLAB and runs under MATLAB. It enables you to acquire live signals from the oscilloscope and visualize them in the frequency domain, including doing things like a power spectral density and a spectrogram display. It allows you to make frequency domain measurements, including relevant peaks, peak searches, occupied bandwidth, SNR or signal to noise ratio, total harmonic distortion, spurious-free dynamic range, and frequency error measurements. You can either execute and use this application straight out of the box if it meets all of your needs. Otherwise, you can customize it with the included source code to meet specific requirements either today or somewhere down the road. To order this, again, it's orderable through Keysight as an application that runs under MATLAB. It's orderable as the N8832A option for Keysight Infinium, which is a Windows 7 based oscilloscopes. That's what I'll be giving you a demo on shortly. Or our Infinivision oscilloscopes, which is an embedded OS oscilloscopes. This application has been available since September, and you can order it either with an instrument or an upgrade option down the road. What's included with this N8832A option is the actual frequency domain analysis application. You do get the modifiable GUI, again the MATLAB source code, so you can customize this to meet your needs either today or somewhere down the road. And you get the MATLAB software environment you need to execute the application, or again to customize it to meet your specific needs. You see at the point on the bottom, this is a software-only product, so you can receive online access to obtain the application, the source code, and the software upon order placement, so essentially through e-delivery. Again, we have two different operating modes. I'm going to be demonstrating mode 1, where you install and use directly on the oscilloscope. Again, that's our Infinium series oscilloscopes, which essentially have Windows 7 PCs built into them. Or you can install this application on a remote PC, either with the Infinium Windows 7 based scopes or primarily with our Infinivision, which is embedded OS scopes. You can connect to the oscilloscope, most likely over LAN, or you could use USB. Again, to summarize, the option includes not only application examples, but also the modifiable application and source code. Again, you can customize this to any specific application or analysis routines you need, either now or down the road. In addition, MathWorks offers consulting services at a separate cost to support the customization or any other application needs you might have. If you'd like to explore this option, contact the MathWorks consulting team at the email address you see on the screen. Okay, I'm going to switch over to the scope now and give you a quick demo, and we'll come back and talk about the N8806A user-defined function application. Okay, now we're going to give a quick demo of the N8832A frequency domain analysis application. As I mentioned earlier, this is an application that runs in the MATLAB environment, gathers data from the Keysight, Infinium, or Infinivision scope families, and then does analysis in the frequency domain. So first things first, you see the Keysight Infinium oscilloscope GUI running. I have just a demo high-frequency clock signal with some distortions built in. You see the overshoot and the undershoot on the screen. This happens to be an Infinium Windows 7 based oscilloscope, so we can run and execute MATLAB and the N8832A FDA application directly from the oscilloscope itself. So I'm going to minimize the scope app. You see I have MATLAB already running in the background. I've clicked on the Apps tab. You see the N8832A frequency domain analysis application listed in there, among others. I'm going to click on it. It has launched, and you see I'm using essentially the internal connection between internal LAN connection between the oscilloscope and MATLAB. So first thing I'll do is I'll test it just to make sure everything's running. We got a connection successful message. That's good. And then what I will do is I will start the application running. Takes a few seconds. The application does run a little bit slower on the oscilloscope than it would on a PC, as the PC and the oscilloscope is also running the Infinium GUI, so it slows it down just a little bit. So you see the spectrum analyzer graph has launched. I'm going to maximize that on the screen here and then just give this a second to update. Now you see what it's done is it basically launched with default parameters, which is bandwidth from 0 to 600 gigahertz, which is well beyond the 33 gigahertz bandwidth that we're using on this oscilloscope right now. So I'll zoom in on roughly the DC to 33 gig area. So I'll hit the zoom button up at the top. I'll take my mouse and I'll draw a box in the frequency area of interest. And now you see I've zoomed in on the signal, which roughly runs from DC and now the zoomed area up to 50 gigahertz, although the oscilloscope, as I mentioned, has a 33 gigahertz bandwidth. So you see the peaks. Again, we're looking at a clock signal, so in an ideal world we should have primarily just odd harmonics, the first, the third, and the fifth. However, you see the second, fourth, and sixth harmonics are kind of strong, as there was some distortion in the signal, as I mentioned. So we could do a couple different things. Again, some of the tools you can use are listed on the toolbar. The icons, we can make channel measurements like adjacent channel power, distortion measurements, CCDF measurements, or peak finds. So let's try the peak find first, again, to take a look at these harmonics. So I'll click on that button. Again, and it'll take a second or two just to launch. It does that, and the default setting is to find the three highest peaks. So you see I have the odd harmonics, the fundamental at 5 gig, and then the third and the fifth harmonics at 15 and 25. You might be wondering why we don't see the peaks marked for the even harmonics. That's because the initial settings of the application are just to look for the three highest peaks. If we want to change that, just click on the settings button. You can change the number of peaks to 6, hit enter, and then again in a second we've now marked and noted all 6 of the peaks, both the odd harmonics you see first and then the even harmonics, and these are listed in order of power. We can also run at the same time some of the channel measurements. So let's say we wanted to look at the occupied bandwidth and the channel power of the fundamental at 5. I can now click on the channel measurements icon on the toolbar. That's again going to take a second to launch, and you see I have that here. The measurement by default is occupied bandwidth. We could also do a chase and channel power ratio, but we'll stick with occupied bandwidth for this example. And then what I want to do, instead of defining it in terms of span, I want to do start and stop frequency. So you see these are the defaults, which are not what we want. What we want is to look at the fundamentals. So I'm going to look at roughly from 4.5 gigahertz to 5.5 gigahertz and make some measurements on the fundamental there. So let's make sure I get the right amount of zeros here. So we want to look at 4.5 gig. Again, give me a minute here while the screen updates. So now I'm looking at the 4.5 gig to 5.5 gigahertz region, and you see the occupied bandwidth of that is 99%. The channel power is around 13 dBm, which equates to the value we saw at the peak here in the peak fine measurement, and the occupied bandwidth of 700 megahertz. So you see you have a very flexible tool. You can do multiple measurements at once, and again, as I mentioned in the slides, you can then take these with the source code and customize them for your individual needs. Okay, now I'm going to switch back to the slides and talk about the N8806 user-defined function. Alright, we're back, and now we're going to talk about the Keysight Infinium user-defined function option, part number N8806A, orderable through Keysight. And as I mentioned earlier, this is an application that runs and executes under the Keysight Infinium software environment. What this enables you to do is use MATLAB to create custom analysis functions for use within the Keysight Infinium oscilloscope environment. It's useful to make new or application-specific measurements, different filter functions. You really have a lot of flexibility with this. MATLAB is included with the N8806 user-defined function option, available with almost all Keysight oscilloscopes. And there's a few examples included: Butterworth, Real-Time Eye. Actually, I believe there's 5 of them. Application examples already included. And the real power of this is the ability to define and execute your own applications in the Keysight software environment. So show you a little screenshot of this. Now when I give you the demo, the screen will look slightly different. We've updated, very recently updated the GUI in our Infinium oscilloscope, so the menus look slightly different than what you see in the screenshot now, but the way you invoke it will basically be the same. You go into the Analyze tab, the Math menu, and a list of functions will show up. The ones that are asterisks are the MATLAB user-defined function examples, but again, you could write your own. You'll basically write a .m script and a piece of glue code essentially between the Keysight Infinium environment and your .m script, an XML file which basically will define the inputs and the outputs for your user-defined function. Okay, I'm going to switch over to Scope and give you a quick demo of the user-defined function. Alright, we're back for our final demo. Now I'm going to give you a demo of the N8806A user-defined function. Again, as I mentioned in the slides, this is an application that runs in the Keysight Infinium oscilloscope software environment and allows you to create customized MATLAB filters and functions that you can execute directly from the oscilloscope GUI, as you see running right now. So the signal I have used for this demo is just a standard PRBS7 pattern running a little over 200 megabits per second. So you see the signal running live on the oscilloscope screen right now. To invoke the UDF, or user-defined function, I'm going to go under the Math tab. I'm going to click on Functions. And again, this menu looks slightly different from the slides. We've most recently updated the oscilloscope GUI, and the slides didn't quite catch up. So you see from the screen we have the capabilities to run 16 simultaneous math functions. Today we're only going to use 1, but we have the capabilities of running 16 all at once. They're grouped, as you can see on the left of the screen, into various categories. The ones with the asterisks are the user-defined functions, and I can see them all by clicking on the user-defined portion of the screen there, and now you see the 5 examples included with the UDF option that are already written for you: a Butterworth filter, an FIR filter, a linear feed-forward equalizer, real-time eye, and square root of the sum of the squares. But as I mentioned in the slides, one of the real powers of this option is the ability for you to run and execute your own custom analysis routines. You would define a filter or any other analysis function as your standard .m script. You need to write a little piece of glue between the Infinium GUI and that .m script, an XML file essentially, which tells the scope the inputs and the outputs, like for this example for Butterworth, the source and the data rate. So we're going to use the Butterworth filter in this example. So I'll source is channel 1, and I'm going to change the data rate to actually a gig per second in this case, and then I'm going to turn it on. And then I'm going to close out the screen. So you can see from the oscilloscope screen I have 2 signals running. The bright yellow is the raw data, the PRBS7 pattern, and then the tan signal is the actual Butterworth filter. So to make this a little easier to view, I'm actually going to split my scope screen into 2 grids first. I've done that, and then I'm going to pick up one of the signals, in this case the live time domain signal, and drag it to the bottom. So now you can see I've got the live time domain PRBS7 pattern unfiltered, and then up at the top I have my Butterworth filter running in real time at the same time as the raw data signal below it. So this kind of gives you an idea of the power of the user-defined function. Again, it didn't have to be the standard Butterworth example. It could be any analysis script that you write. You would copy that and the XML file that I mentioned before into the scope's math directory, and then your custom function would appear in the math menu under the user-defined category. It would appear in this boxed area here. So that concludes our demo for today. I'm going to turn it back over to Rob for a wrap-up.
Thanks, Neil. Let's wrap things up with a summary. There are a few reasons why you would want to use MATLAB with Keysight Instruments. If you have some advanced analysis or visualization capability you'd like to develop, or if you'd like to develop an application that makes use of Keysight instrumentation, MATLAB can be a great tool to extend the built-in capabilities of Keysight Instruments. You can also use MATLAB when you're working with customized measurement and analysis routines. For example, custom waveforms or modulation schemes, just as a couple of examples. MATLAB is a great environment to really customize your routines based on your own needs. And then finally, as we've seen in a few of these examples today, MATLAB is a great tool for automating measurement and analysis tasks using Keysight Instruments. And MATLAB is also a great tool at generating reports that document your results and summarize your testing. These are a few reasons why you may want to use MATLAB with Keysight Instruments. There are a number of resources available both on the Keysight website as well as the MathWorks website. On either page listed here, you can find application notes, links to drivers, examples, and other great resources to get you started. If you would like to get access to the MATLAB software to start trying these things out on your own, you can also request a free MATLAB trial on the MathWorks website using the link on this slide. That concludes today's webinar. Thank you.